Lab 4 Magnetic Braking with Faraday by Shervin Praveen. Intro. The purpose of this lab is to create a computational model of magnetic induction and compare it with an experimental model. We find that we are able to accurately predict how the aluminum foil interacts with the magnet. Fundamental principles. The main principles we will be using are Faraday's law, Biot-Savart law, and Newton's laws. Faraday's law shows us the relationship between flux and EMF. Biot-Savart law shows us how magnetic fields are generated. Newton's laws help us predict the motion of the magnet. Experiment. We begin by recording our initial conditions. We first measure the aluminum foil's geometry to track with our code. Then we include the magnet's properties, such as the magnitude of the dipole moment. After taking note of the measurements, we then measure the time it takes for the magnet to drop. Properties and dimensions. The length of the tube of aluminum foil is 0.27 meters. The width of the foil is 0.0031 meters. The inner radius is 0.019 meters. The magnitude of magnetic dipole moment is 4.523 amps times meter squared, and the mass of the magnet is 0.023 kilograms. The average time it takes for the magnet to reach the ground after going through the aluminum foil, we measured many times, was 1.342 seconds. Coding. In this page are our initial conditions. In the top left, we define our constants. In the top right, we inputted the measurements we took from the previous slide. This is the geometry of the tube of aluminum foil. In the bottom left are the properties of the magnet, which include the mass and the magnitude of magnetic dipole moment. And in the bottom is our code for visualizing the bar magnet and creating our unit vectors. This is our computational code. In the top left, we have our initial condition for velocity and time. The second line of code, we create a function for the magnetic field from the magnet to any point R. The third line of code is a function for the rate of change of flux, which is the time derivative of flux. And the last line of code is our total forces, which is F net, which include the force of gravity and the magnetic force. Results. This is our velocity versus time graph of the magnet. As you can see in the beginning, there's a steep drop due to the force of gravity, but the speed does decrease, and this is due to the magnetic force. After this, we see the velocity stays constant, which indicate the F net equals 0, which means the force of gravity equals the magnetic force. Near the end, we see the speed increase again, which indicate the magnet has left the aluminum foil. Experimental questions. What happens if we flip the magnet? If we flip the magnet, the induced current would flow the opposite way, which would create a magnetic field which would oppose the magnet either way. This means it doesn't matter which way we put the magnet in, the magnetic force would still slow down. How does the time differ from the model, and how can we make it more accurate? The times are not exactly the same, but we can make it more accurate with consistent and perfect setups, such as getting accurate temperature or perfect aluminum foil rolls. What does the shape of the graph tell you about the forces? As we can see in the beginning of the graph, the force of gravity is the only thing acting on it, but during the horizontal part there must be something opposing gravity, which would be the magnetic force. And near the end we can see, since the speed increases again, it's only the force of gravity. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? With the resistivity as close to 0, the induced current would be very much higher since there's no resistance, and this could slow down the magnet even more or even make it stop. What if holes or slots were cut into the tube? How would this affect the ring currents in the model? In the code, we represented the foils as coils. Damaging a coil could restrict the current flow, making the induced current weaker. Thank you.